Have you ever wondered how we predict things that seem, well, totally unpredictable? I mean, think about it. From the global economy to the weather, our world is just full of these complex systems that don't play by simple, straight-line rules. So in this explainer, we're going to dive into the powerful techniques engineers and scientists use to build mathematical models of these very systems so we can finally understand them and maybe even control them.
Yeah, it really all boils down to this one big question. When a system doesn't follow a simple, if you do this, you get that kind of rule, how on earth do you build a mathematical model that can actually describe what it's going to do?
Right. Take the global economy. A tiny little change in interest rates in just one country can create these massive cascading effects all over the world, effects that are not always easy to see coming. It's a perfect example of a complex system.
Or hey, just think about the weather. Meteorologists have gotten so good at forecasting, but we all know it, right? Some tiny little shift in atmospheric pressure somewhere can be the difference between a beautiful sunny day and a massive thunderstorm. It's that classic butterfly effect.
And you know, this isn't just about giant natural systems. Even something we've built ourselves, like a modern car engine, has these incredibly complex interactions going on. You've got fuel flow, temperature, pressure, and none of it is simple. So all of these things are what we call nonlinear systems. And in simple terms, that just means their output isn't directly proportional to their input. So doubling the input doesn't mean you'll double the output. Nope. It might triple it, or it might do something completely unexpected. And that's exactly why we need a special set of tools to figure them out.
Okay, so let's get into it. The official name for this whole field is nonlinear system identification. But you know what? I like to think of it as being a system detective. It's like you're investigating a mysterious system to figure out the secret rules that make it tick.
The formal definition here tells us it's all about building these mathematical models from data. So as the detective, you're not just taking wild guesses. You are carefully observing what goes into the system and what comes out of it. And from those clues, you start to piece together a working theory of what's really happening on the inside.
Now this is where it gets really interesting, because this breaks down the detective work into 4 clear steps. Let's walk through it. First, you gather clues, which just means collecting data. For that car engine we mentioned, this would be recording stuff like fuel consumption, engine temp, and speed under all sorts of conditions. Second, you choose your tools. This is all about picking your model architecture, basically deciding how you're going to solve the case. Are you going to use a simple equation or a super complex neural network? It's like choosing between basic logic and a full-on forensics lab. Third, you build your theory. This is where you estimate the model's parameters, and parameters are just the specific numbers that make your model fit the clues you've gathered. This is you connecting the dots. And finally, the moment of truth, you interrogate the theory. You test your model against brand new data it has never seen before. Does your theory hold up? If it does, you've cracked the case.
Now, our system detective can take one of 3 main approaches, and really, the choice just depends on how much you already know about the system you're investigating. These are called white box, gray box, and black box modeling. So let's look at the 2 extremes. A white box model is when you have the complete blueprint. I mean, you know all the physics, all the equations that make the system work. Then on the other end, you've got the black box. Here, you know nothing about what's going on inside. All you can do is watch what goes in and what comes out, and let an algorithm, like a neural network, try to figure out the pattern. And honestly, this is where a ton of modern AI lives.
But you know, in the real world, the best answer is usually somewhere in the middle. As the author Oliver Nell says right here, the perfect model isn't always the most practical one. This is where the gray box approach comes in. You combine some of the physics you already know with these data-driven techniques. It's often the sweet spot for getting fantastic results without spending years and years on development.
Okay, so why go through all this trouble? Why play a system detective in the first place? Well, because once you have a model you can actually rely on, you can do some incredibly powerful things with it.
And this is where the rubber really meets the road. With a good model, you can use it for prediction, forecasting things like stock prices or energy demand. You can use it for simulation, creating a digital twin of a jet engine to test it to its absolute limits without ever leaving the ground. You can use it for optimization, tuning a car for the best possible fuel efficiency. You can use it for control, building the smart systems that act as the brains for something like a self-driving car. And you can even use it for fault detection, spotting when a machine is about to break down, which can save a ton of time, money, and maybe even lives.
This field is always changing, and right now, it's sitting at the absolute heart of the AI revolution. Let's just take a quick look at how the latest breakthroughs are totally transforming the world of system identification.
You see, when the first edition of Nella's book came out, the world looked pretty different. The second edition's preface points out that the invention of deep learning has completely changed the game for black box modeling. It lets us tackle systems that are way more complex than we ever could before.
So one of the most exciting new tools in the detective's toolkit is something called a long short-term memory network, or LSTM. Just think of it like a neural network that actually has a memory. It's fantastic at understanding sequences of data over time, which makes it an incredibly powerful tool for modeling the dynamics of complex systems, like, say, the weather or a fluctuating stock market.
And at the end of the day, all of these concepts are more relevant now than they've ever been. I mean, the principles of system identification are the bedrock for so much of the tech that's shaping our world, from those enormous climate models trying to predict our planet's future, all the way down to the AI powering the smart assistants in our pockets.
So this explosion in our ability to model things leaves us with a really powerful, kind of profound question. With these new tools, we are getting so close to being able to model almost any system we can observe. The question isn't so much, can we model it anymore? It's what are the most important problems we should be pointing these incredible tools at? Now that's something to think about.